So we're going to start the sort of main topic, which is linear models or multiple linear regression. And so today, hopefully, we'll discuss the setting and maybe a bit of estimation. Geometric interpretation comes next. So there are two parameters, beta and sigma squared. We talked about estimation. There's some associated matrices that we talked about, the hat matrix that you have seen in your work problems and Gram matrix. And then we talk about statistical properties of these estimators. Okay, so let's start with the definition or the setting. So how many people know what linear regression is? No, so multiple linear regression, like also like simple linear regression, you probably know. So maybe someone tells me what regression is, what linear regression is. What is the problem that we're trying to solve by regression? Yes. Okay, so maybe, so what was your name again? Can you like remind me? Joseph. Okay, yes.
It's not like fitting a model to set up data used for like predicting other data points.
Fitting a model to a set of data for the purpose of predicting, what was that again?
Like predicting other data.
Predicting other data. Yeah, so these are all good. So fitting some model to data for the purpose of prediction. Okay, so if you want to make it a little bit more precise, what do we mean by fitting the model? So what is the data actually? So what kind of data we have? Okay, so there's some kind of independent and dependent variables. So that's usually the name that people use. I'm gonna not necessarily say independent and dependent. So you have a set of features or covariates. Features, covariates. Features is what people in machine learning use. Covariates is what statistics use. Independent variables, which I don't quite like. It's another name. And then you have something which is like the target, it's the ML terminology, or response. It's another variable, or like dependent variable. The reason why I don't like the independent and dependent terminology is you can switch them. So later you can like treat Y as the independent variable, try to explain X. So it's like up to you. But for the purpose of regression, there is like one target, one response we care about, we want to explain it. This notion of explanation is, again, not precise, but that's what we want to do. So we want to explain it based on this xi, or the features. And so we have this pair, and we have I from 1 to n. That's to say we have like a sample x1, y1. So this is observation 1, x2, y2, xn, yn. So you get to see n copies like for different, let's say, individuals. Let's say, for example, yi is someone's sort of, I don't know, income in 10 years. And xi's are a bunch of features that you have about them. Okay, so their double education, their current age, there's like socioeconomic background and something like that. So you want to predict what their income would be in the next 10 years based on this information. Okay, and so these are individual people. There are a lot of other cases, but so this n is, what is n called? Sample size. So n is like the number of observations that we have, and it's the sample size. So we want to explain yi based on xi, and you're going to assume that there is sort of some constant relation. So there's a relation that explains xi or like yi based on xi that is the same for all these people. Okay, so this relation doesn't change. So if the relation between yi and xi changes for every individual person, that's a little bit more challenging. Okay, so we might be able to do that, but for the start, we're going to assume that's what the relation between xi and yi remains constant, i.e. does not depend on I. Okay, so how do I model this relation? A very general idea. So how do you model it? Let's say I ask you guys. How would I go about like trying to do this? So this is the goal. How would I achieve this?
So it's like y is equal to beta 0 plus beta 1.
Yi is equal to beta 0 plus beta 1,
X1.
x1. How about the I? What happened to the I? You can say xi, let's say. xi1.
Yeah.
Okay.
Plus the beta sets I is 0.
xip. Okay.
Plus
Plus some error term. Okay. This is p. This is good. Okay. So we got there in one step, but I wanted to do so xi, xi1, xi2. So each of these features is like a feature vector. You have p features basically. So this could be their age. This could be something else. Their height maybe it has an effect on their income. Like some other like the cholesterol level. And then a general model, a more general model would have been like, I would just have a function of these xi's plus some noise. And this function is constant. Okay. So that's a more general model. It's like more general model. So if you assume that f, so this f maps Rp, their p features, to R, because you're usually going to assume that R, like yi isn't real. So, so I'm going to assume that this is in R, this is in Rp. Okay, so p features. So f maps from, so this would be in R, this is in Rp, this is again in R. In Rp. So if you assume that this function is linear, so the general linear function can be written as, so if anyone remembers what a linear function is, so we talked about linear operators, right? What a linear function is. So if we assume f is linear, then we get linear regression. So what is a linear function?
classification plus type addition.
Can you say it again?
Like it contains like multiplication and addition.
There was a more abstract way of defining it. So if I remember like what a subspace was, like a linear subspace. goes under addition and scalar multiplication, what was a linear operator? Yes.
A mapping from one subspace or space to another subspace.
So a mapping from one subspace to another subspace. What was your name?
So
So, okay, so mapping from one space to another space, that's like a general operator. So how would it be linear? So is there something else that I have to assume to make it linear?
formula.
Sorry?
I only remember the formula. So for FCX equal to CFX.
F, how can I write CX? What do you mean by CX?
C is a constant, X is
Oh, something like that is,
equal to C from Fx. And Fx plus 1 is equal to Fx plus X.
plus Y?
Y.
Yes. Okay, good. This is the definition. Okay, so so here is like a constant. So F is linear. So it commutes with linear operations. So if I multiply a vector by C, it comes out, not C of X, just C of Fx. Yes. And then if I add two inputs, the F would be the sum of the two. Okay, from this, it follows that F can be written as like a matrix times X. Okay. And in this particular case, because X is in RP and the output has to be in R, so what will be the dimension of this A? Sorry? It's just like in R, so it would be 1 times P. What was your name, by the way? Luigi, okay. Right? So it's like, you want a function that does this? We talked about that, like, we haven't proved it, but a general function, it looks like this can be written like A times X. And because F in our case maps to R, so that has to be 1 by P. And so this we call like one like beta transpose. Okay, I'm going to call this beta transpose because you have a vector, you transpose it, that's a general 1 by P matrix. Okay, so a general linear function F from RP to R can be represented as F of X is equal to beta transpose X for some beta in RP. Okay, so we start from this general model. We assume F is linear, then F can be written as like something like that. And that gives us the linear model. So start from star, impose linearity assumption on F, we get that yi has to be like beta transpose xi plus epsilon. So that would be our F of xi basically. Okay. F has to look like that. So plug it, we get this, and this expression is exactly the same as this one. So what was your name, by the way?
Alex.
Alex. So the one that Alex mentioned. So this, if you look at the one at the top, is exactly the same as this. So why is that? Why are the two highlighted? Well, it's the same. Yes.
Beta transpose times X will create a constant and just matrix multiplication of X.
Yeah, so if you do the matrix multiplication, basically this beta would look like beta 1 up to beta 2 up to beta p. And remember, xi is just xi1, xi2 up to xip. So when you do the transpose of this multiplied by that, you just multiply each coordinate, beta 1 times xi1 plus beta 2 times xi2 plus beta p times xip, and then you sum them up. So that would be the third one at the top. So the one at the top and the one at the bottom are exactly the same. Right. So this gives you a little bit more context where the linear regression comes from. Generally, this is not a bad assumption, assuming that yi is some general function of xi plus noise. That's a little bit of assumption. You're assuming that the noise is sort of additive. But at this point, you're not assuming anything about the noise. So this is pretty general because I can define epsilon I to be just the difference, yi minus f of xi. When I impose more assumptions on it, then this gives us some restriction on this model. But then the main point here is I'm making a very strong assumption on f. Okay. What is the very strong assumption? It's that it's a linear function. Okay. And this in general is not true. So the majority of this course is not true. So why would we do this? Because it's a very good approximation oftentimes. And it's a very simple model. The first thing that you try, oftentimes it does a good job, but you can be rest assured that probably like 99% of the time, a linear model is not true. No model is sort of true, but it's a very good approximation. Like this is like a philosophical question. So all models are wrong, but some are useful. It's like, I don't want to go there, but it's a very good approximation, although it's a very simple model. But it's a very strong assumption. I just want to emphasize that this is starting point is a very strong assumption that the function is linear, which may or may not be true. Oftentimes not true in the strict sense. Sounds good? Keep this in mind. This is the main assumption. So if someone asks you about what are the assumptions of the linear regression model, the main one is that it's a linear model. Okay. All the other things are like secondary. This is the big assumption. What else? Questions? What else can we say here? Are we done? So we're done with linear models. So what is the next step, let's say? Yes.
Graph it.
How do I graph it?
That's the question.
Yeah. So it's a multivariate. Like I'm talking about a multivariate function, so it's a little bit hard to graph. You can do it in the case where you have p is equal to 2, let's say. Actually, it's easier to do it when. Yeah. So let me maybe point out that oftentimes you add like a intercept, add an intercept to the model. So you would, okay, so these weren't exactly equal, so I should mention. So if you drop this beta 0, then they would be equivalent because you compare, this would be beta 1 times xi1, beta 2 times xi2, beta 2 times xip. And that wouldn't have the intercept. So beta 0 is the intercept. How can I get the intercept in this format? Let's first do that. Good. So that's the trick. So we usually like add like a constant feature. So everyone gets this one feature, the same for everyone. xi2 up to xip. And then I can like expand beta to include beta 0. Beta 2 up to beta p. So when I multiply things, so the model is still the same. So this is exactly the same. Then I take this beta transpose xi, which you may also recognize as the inner product of beta and xi. So this is also beta inner product with xi, you remember? Then I get beta 0 multiplied by 1, beta 1 multiplied by xi1, and so on. So this little trick, augmentation of the feature vector, gets us there. And so oftentimes you see that we talk about like p plus 1 dimensional features and p plus 1 dimensional parameter. So this is why we have this p plus 1. you can call it like D, let's say if you want. Let's not carry out the one. But often you see that you have P plus one features, P plus one. So P real, like true features, like genuine features and ones that you added. So in the case where P is actually equal to 1, so this is called simple linear regression. Right, let's try to graph it because you guys suggested. Simple. Yi is equal to beta 0 plus beta 1. I plus epsilon I, that would be like the, like I'm going to do okay, xi1. So there's just one feature. So beta would be beta 0, beta 1. Xi would just be like 1, xi1. And this, I'm going to put like a bar here to emphasize that these are vectors. So a simple linear regression, this one I can sort of easily plot, and you probably know you can do a scatter plot, right? So I can do a scatter plot of xi1 versus yi. So what is a scatter plot? So you have I from 1 to n. You just plot points, right? Xi, like pairs of xi1, yi. So I would have one point here which has like xi, like x for some basically I have xi1 and y1. I plot that for another point, for another I would get something like that, maybe that. So there's going to be some line here. And if the model is sort of true, what I would get is like these points are going to be usually around this. Okay, that's what you'd expect to see. Right. So what is that line? Sorry? Yeah, so the equation. I hat. Let's say this is like an equation. So let's say this is call this x, call this y. So mathematical equation of this line is y is equal to beta 0 plus x, right? It's beta 0 plus beta 1x. So that's the line. So why aren't the points on this line? Exactly, let's say. What would happen if they were all in this on this line? Yes.
Epsilon will be 0.
Yeah, so if you had no noise, so you'd expect this like all of them to line on this line. Okay, because this is a linear relation. So the location of all these, this part, so if you plot yi versus this, they all satisfy this equation, so they have to be on this line. So this green line is the location of all x, y pairs that satisfy that equation. So the reason why they're scattered around is because of this noise, let's say. I'm assuming that there is some noise. Okay, so you probably have seen this. And in higher dimensions, it would be like a hyperplane. So this is called the regression line if you want. Generally like regression function if you want. And then this would be like a, so the equation would be a hyperplane. And then either things are on, so in two-dimensional case, it would be like a plane. In higher dimensional space, it's like an extension of it, which is called hyperplane. It's just that these are called affine spaces. It's like linear space, but shifted. So if it passed through the origin, it would be a linear space. So lines that pass through the origin are one-dimensional linear space. So this would be an affine space because it's like a shifted linear space. So affine hyperplanes are the hyperplanes are affine subspaces, and the equivalent of the regression line would be a hyperplane. So things would be scattered around that hyperplane. It's a little bit hard to visualize in more than 2D, I would say. Sounds good. So we plotted it as you requested. To what else? It's always good to do some sort of plotting if you have data, especially in low dimensions, to visualize. So for example, if I plotted this data that I have, and I would observe something like this. Would that be like a linear model would be a good model? Probably not, because like it shows there would be like a curve here, not a line. So you plot in a scatter plot, it gives you some idea what you're dealing with. Okay. This you can still do like a linear regression, but you have to add like other terms. Maybe we can talk about that later. So like the things that we discussed is going to allow you to do this. Anyone knows how to do this? Like, looks like a quadratic function. How can I reduce it to sort of a linear regression? Say things were around something like maybe a quadratic function here. This is like off the road a little bit. Right? Has anyone seen something like this?
Just beta 0 plus beta 1 times like x to the power.
Beta 0 plus, can you say that again?
Like beta 1 times x to the power.
2, right. So I would include this first term that we have. I would add another term, beta 2, xi1 squared. So you add a quadratic term plus x epsilon I. Okay, so this equation is now the equation of like a quadratic function, and potentially allows you to like have this like, curved shape. Okay, so this would still fall within our like framework, because now I have this would be my new beta, and xi would be like x like 1, xi1, xi2, like it's xi1 squared. Okay, so I just augment the features by adding like a quadratic term to the like a quadratic version of my original features. So you can construct features, new features from your original features, and a linear combination of this gives you like a function in X which is non-linear. So it's flexible. It's not as restrictive as it may seem at first. But adding this, you can see you're adding a bit more complexity to your model. So you have more parameters here. If the model is really this, then you don't need that term. But this model includes this as a special case, right? This is a better, like not better, like bigger model. Why this model includes the first one as a special case? How can I get the first one from this model? Yes.
Just make that like equal 0.
Yeah, so if you set beta 2 equal to 0, you get back the original model. So this model subsumes or like includes this as a submodel. So this relation we'll talk about. So this is, imagine like all the relations that you can get as you vary beta 0 and beta 1. These are all linear models of this class. These are included in all the models that you can get as you vary beta 0, beta 1, and beta 2. Because for some of them, this is 0 and this is that class. So this class of all models that are described by this relation is a bigger class that contains the models that are described by the original. And a lot of like statistics or like interesting things in the statistics is how to decide how big your model has to be to capture the actual relation that's there. So we'll talk a little bit about that towards the end. A lot of the tools that we develop like implicitly try to answer this question with this question of model selection. So if you have a set of models, how do you choose like a good class of models or a good model? Good. So back to the main road. So what should we do next? So what do people usually do next? So you get some data, you have some assumptions like this. What do statisticians do? Is that the end of the story here? We imagine some model, we have some data, we plotted something. What is the main job?
Check conditions.
And we haven't introduced the conditions yet. But yes, if you have, so let's say if you want to do the linear, testing the linear assumption is hard. I haven't introduced that, but we'll introduce the conditions. So I have to introduce conditions, maybe some conditions, but there's a more interesting job.
Like see if the model's a good fit of the data.
See if a good model is a good fit of the data. Yes, that's main job. So how do we do that? Sorry?
The arrow term.
Minimize an error term. So what you want to do is actually fit this to the data. Okay. So this is a large class, beta 0 and beta 1 can be anything. I want to figure out which ones actually fit this case. So what is the beta 0 and beta 1 that works in this case? What is the best beta 0 and beta 1? So what is the closest within this class of model to my data? Okay, so I have the data. I've postulated a class of models. So I can vary beta 0 and beta 1. If I vary it, for example, I would get something like, this is also like another line in this class. This is not a really good fit. There is one in this class, a particular beta 0 hat, let's say beta 1 hat that fits my data well. And that's what I want to find. And then I can decide whether I'm a good fit or not. So this goes back to the problem of fitting the model or like estimating the parameters. Okay. The next step, usually like the main thing that the statisticians will do is try to estimate the parameters of the model. Another way of saying is fitting the model. Okay, so estimating the parameters, i.e. fitting the model. There was another point is like checking assumptions, so we can make more assumptions before checking. So there's another point which is goes in parallel, because if I make more assumptions about the model, it might ease my job of estimation. Okay, so let's say assumptions, more assumptions. Before checking them, we have to put assumptions, more assumptions. Say on the noise and xi's, etc. Okay, so we can do that. But let's, so usually like in this course, I'll make more assumptions, then I do estimation based on those assumptions. But since we can do estimation even without further assumptions, okay? So there are some reasonable things that we can do. So there was a point here that you mentioned. So what was that? So minimize, is that what you mentioned? Or someone mentioned minimize something. So minimize what?
The arrow term.
So what is the error term?
So the last term of the arrow term.
Right, minimize. So I want to make a distinction here. So that is going to be very confusing, and I'm going to leave it like confusing for a while. So there is like in a statistic, at least the frequentist version that I'm going to teach you, there is like a model. There's a true model. In that model, there is this epsilon I, which I don't see and I can't access. Okay, so I'm going to assume, sometimes I write something like this. Yi is like beta 0 star plus beta 1 star xi plus epsilon I. Because there is a true beta star 0. There is a true beta star 1 and I can see. And there is like a noise here that I can't see. What I get to see is xi and yi. But I'm going to assume that they've decided that this relation, maybe with some assumptions on the noise. Then there's the regression model that I usually like impose, that there's like beta 0 plus beta 1 xi. Sometimes we write it like this because I don't care about the rest. And in this model, the beta 0 and beta 1 is up to me. I can vary them and think about them. And then the error in this case would be like, what is the difference between these two things? Okay, so sometimes it's called the residual. People sometimes call that the error, the unobserved error. This is the residual because I can form this and look at it. Okay, so this is the residual. The I, let's say. It's like it's not exactly the residual, but residual is the one that you get for the best fit, sort of. But I'm going to look at this difference, like potential residual. And then you minimize what? I can't minimize this because I have a bunch of terms here which are dependent on. So what should we minimize? So I'm going to look at this error. Potentially, if this is small for every, so if I choose beta 0 and beta 1 such that this is small for all i's, then I'm pretty good. Okay, so this difference here in this case would be like how far this is from this line, like the vertical distance of the point from the line. So the vertical distance of the point is yi from this position. So from the x-axis is yi. Okay, the vertical position of, it's like this point is this guy. It's on the line. So the difference is that how far I'm from this line. So if you try to minimize all these distances, then you have a good line. Okay, but there are a lot of them, right? So how do we like with a minimization? I can't just pick one. What do we do? Sum them. Okay. So if I sum them, it's not going to work. Why wouldn't it work? There are positives and negatives. They could cancel out. I can get something really small. So I want the absolute value sort of to be. Yeah, so like the simple thing would be to put an absolute value, and this works. Okay. I can minimize this, but it's a little bit harder to minimize. There's no closed form. I can like do it by numerical methods. Is there like Gauss or like people attributed to Gauss, like Gaussian everything. So they decided to square things. So you square, then this problem has a closed form solution. Okay, and this has the property that gets rid of the sign. So if this sum of squares of this sort of error that you want is a small, then I'm sort of minimizing everything in a sense. But this choice is up to you. Okay, so you can change it and still get something. But the one that people often call linear regression fit, or like the usual ordinary least squares, is the one that minimizes. So if you minimize or beta 0 and beta 1, the beta 0 and beta 1 that you get, the solution is called ordinary least squares, OLS. Okay. Ordinary least squares. You would write something like, I'm going to write it argmin. If you remember, I've introduced this before. Yi minus beta 0 plus beta 1. It's going to be beta 0, beta 1. I'm going to write it as beta hat 0, beta hat 1. So argmin, anyone remembers what argmin means? So this is like mathematical way of writing it. Yes, exactly. So this is the argument, like the beta 0 and beta 1 that minimizes this. If I put a minimum, it means like the smallest value the objective function takes. I don't want the minimum. I care about it, but not as a primary object. I care about the points, like the solution, basically. So that this is why like people use argument. So the argument that minimizes that is just going to be like the optimal beta 0 and beta 1, or beta hat 0 and beta 1. Okay. It's called least squares because it's the least like squares of errors, something like that. And minimize the square, like sum of the squares of the errors if you want. I for one. Okay. This gives you like a starting point. now you have like an estimate. So we can call this a fit. So this gives you all the information you need. Now this is the best within your class in a sense. You haven't defined best, but according to this criteria, you find the best within this small class, which is like the best data 0 and data 1. Sounds good. This is still not quite statistics. Like this is like the beginning. This has been done a very long time ago. It gives you a good fit. You can predict future, like if the goal is prediction. So originally this was like evolved, for example, to predict the location of certain planets, maybe. Okay, so you have some data, and then you like, I actually don't recall exactly, but if you plug in the future xi, you might hope to get the future yi. So this can already be used for prediction. So if I have this regression line, which is, so this thing is called, it's like beta hat 0 plus beta hat 1 xi1. This is, or like, okay, I'm gonna write it as, yeah. So I'm gonna, this is actually called the fitted value. Mu hat I. There is this regression line or regression function that they sometimes write it as mu hat x. If you want mu hat x1, if you want. Let me drop I here, 1 here, because we just have 1 here, and this is like simple linear regression. I'm going to drop 1. Here we're assuming that xi is actually in R. So this would be the fitted value. So these are the mu hat i's are the ones that are on this line. So this is yi. This would be, after I fit it, this would be mu hat I. Okay, this would be yi, and the difference would be the residual. So this difference, the optimal sort of distance in a sense, this is going to be called the residual. So it would be the yi minus the best fit. And then there's this regression line, which is beta hat 0 plus beta hat 1, and then there's some generic x. Okay, the difference here is that here I'm evaluating it, this regression line, but for the features that I've already observed. Okay, so this gives me n data points on this line, not in the data point, but n points on this line, which are like the fitted values for these observed x's. But this model now has a general regression line, which is just the equation of that line. Now I can plug in new x's, the x's that I haven't seen, and it gives me some prediction of what the value of y is. So that's how you can use it for prediction. That was the original intention. We wanted to predict. So this gives me the relation between x and y, that linear relation, and then it can be used. So regression line slash function can be used for prediction. I'm going to assume that you know what I mean. Okay, if it's not clear, let me know. Okay, so you've seen some data already, but if someone else comes up, gives you the x of some new data point, doesn't give you y, that corresponding yi, you can predict. You can plug that xi into this, and you get a prediction of yi. You don't get the exact yi, but you get something hopefully close. So that does your like prediction job. Okay. At this point, it's like we are doing a little bit of statistics, but not true statistics. So this is like pre-statistics. Okay. But it does the job. Okay. It's like if you're like doing machine learning and you care about prediction, and this is sort of good. There are metrics that you can measure how well you do, because sometimes the data points that you see, they're called training data. So you trained your model. So fitting in the ML terminology is called training. So you train your model on the data. A statistician called fit it to your data. You get good predictions on your data that you feed it to. Okay, so you're gonna get good predictions, hopefully, on the data points that you already have, because you specifically minimized over those data points. But you may not necessarily get good prediction on the data points that you haven't seen, especially if like things are like on the margins of this. So you've seen a lot of data here, but you haven't seen like data points here. Maybe this is linear here, but then it goes like that. Okay, so you haven't seen this part. Especially for extrapolation, things like this, things could go wrong. So there are techniques in machine learning to try to assess the prediction performance. So you're not still like done, even if you're like doing machine learning. But statisticians care a little bit about more. We'll talk about that more. Okay, so we'll talk about what we like statisticians traditionally at least cared about. So is this sort of okay so far? Sounds good. This is like things that has been like done in like 1800. Okay, so we're there. Not yet into the 20th century. Questions? So this I did for the this problem is called least squares. Okay, so least squares. Since I write it as LS, so we solve the least squares problem to fit them all, or estimate the parameters. How can I generalize it to the multiple linear regression or like general P? So this was just a single. So if I want to do, so we did the simple linear regression case. If I want to do this more general setting, can I use the same ideas? Yes.
Sum it up for all the questions.
Sum it up for, okay, great. So that's one way of doing it. So you get summation. So how to generalize? To P bigger than 1. So I would have argmin beta 0, beta 1 up to beta P. I have summation I from 1 to n, yi minus, this is going to be beta 0 plus beta 1 xi1 up to beta P xip. So that's the regression part. Squared, well, actually, we don't have to sum over all dimensions, so this is going to be in there, right? That's going to be like if you meant that's sort of. So this is the error. Then okay, just update this part by adding everything. If you're a little bit more like compact notation, like I do, so I do it in the vector form. So xi. So you get yi minus beta transpose xi. This is a little bit more cleaner, I would say. Right. So yi is supposed to be close to this plus some error. So this is the linear part minus yi squared. That's the error squared. And so argmin would be beta hat. So instead of doing something like this, which is like very extended, let's say, format, we do it in a compact form, exactly the same thing, but so that would be our least squares problem. Okay, it's just the same idea. This part just replaces this regression part, and the regression function after fitting would be, it's not going to be a line anymore, but more general linear function would be beta hat transpose x. The beta transpose x was our original function. Now we have beta hat transpose times x. So if I get a new data point, I just plug it in here and it predicts me the new value y. Predicts for me. Sounds good. Is there even a more compact way that I can write this? Yes.
the transpose, like the z squared, you do like yi minus b transpose xi transpose times the.
Okay, so let's try writing what you're saying. So so you want to write which part, this part or?
Yeah, so that part transpose times
Transpose times itself?
Yeah.
Right, this works, but it's a little bit because this is scalar, the transpose itself. So transpose in this case doesn't help. It is on the right track though. Very close, right? I want to write it in terms of the norm, let's say. So give me something in terms of the norm of a vector. Can you do that? Remember what the norm, yes.
The norm squared is BTX is just inner product.
Norm of what?
The norm of
You have to give me a vector.
yeah, the norm of
I'm going to help you, like y1 up to yn. I write it as a vector.
right. So if B beta transpose times x equal to that, then you just norm of that line.
If it was equal to that would be 0, then I would have been saying. I want to minus something, right? Minus beta, okay, beta transpose xi up to beta transpose x1. Beta transpose x2, beta transpose xi. So if you imagine this would do 0.5s. Subtraction. Now, if I take the norm of this, that right? So the norm squared of this would give me y pi minus beta transpose xi squared. Because I'm going to square each of these, and then I added them up. Okay. So I'm going to call this vector y. Now I want to write this in a bit more compact form. Yes, I don't quite like. So how do we write it in a compact form? I have to help you guys a little bit because there are different ways of doing it. I'm going to rewrite this as xi transpose beta, x2 transpose beta up to xn transpose beta. So why can I do this? I get some approvals. Why can I? You can say why that was.
Obviously, it's just like the dot product to it.
Yeah, so it's dot product, it's sort of symmetric. It doesn't matter if I do it this way or the other way. So imagine this, you just multiply each entry and then add up. Doesn't matter if you multiply this by that or that by this. Because a scalar, another way of saying it is like beta transpose x1 transpose has to be equal to itself because it's just in a scalar. And if you do the trick of doing transposition, so this is going to be x1 transpose beta transpose transpose, which is just beta. Okay, so this is like formal proof because a scalar has to be the same as its transpose. If you do it, you get that. This uses the fact that the transpose of product is the product of the transpose but flipped. And this equality is because beta transpose xi is just a scalar. In any case, this is easy. So I'm going to do that. And then I want to write it in form like this, a matrix times beta. And I do that.
there's gonna be only one row with S1, so that's P.
One row. Now, if it's a one row, then one row times a vector is just going to be a scalar. I have n. So this is an n-dimensional vector. So how many rows do I need there? N. You need n rows of these if it's going to work. And what do you guess those rows are going to be? So this is like p by 1. If I have 1 by p, this row gets multiplied by that. Works out. Anyone knows what that row should be if I want to get this as the first element? One column, I mean this.
Yeah.
This doesn't, I mean, from what I wrote, this doesn't follow, but like let's follow what I wrote so far.
So it should be x1.
Yeah, so x1 transpose is like a row vector, it's p-dimensional. And if you multiply this row by that, it's just x1 transpose times beta, that would give you the first element. If I have x2 transpose, this row gets multiplied by that, right? That's how matrix multiplication works. So if I put a matrix like this there, it would work. Right? So if I call this matrix X, capital X, this is going to be X beta. So in the end, this was Y. This is going to be X beta. So what I get is the norm of Y minus X beta, basically, is what I'm looking at. So if I argmin or beta, that would be the least squares problem. So this is exactly the same as this one, but even more compact. So this X matrix that comes from this argument, this is called, anyone knows what this statisticians would call this? We call it the design matrix. Okay. So it collects all the feature information as the rows. Okay, so each row would be the feature vector or the covariates for one observation. So you have n observations, so it would be n, and then their p features, so it would be n by p. Okay, so that's how it would look like. Oftentimes it would be n by p plus 1, because we're going to have often, we also have the intercept. Right. So I would add like a feature of 1. If I add a feature of 1, I have to add 1 to every row, like the first. So this is like my additional feature. So I would have 1 here and this. So you get that column of all ones that was mentioned. So I get column of all ones and then these xi's. So that would be now in our n times p plus 1. So usually you have the columns of all ones. This is one view of the design matrix. Sounds good if I had an intercept. So that would be that. And then the beta would be like beta 0, beta 1 up to beta p. You can like verify that exactly the same thing happens. Then you multiply. If I multiply x by this, the first row gets like 1 gets multiplied by this, the rest gets multiplied by that, so I get the intercept that I want. Okay. There's another view that we often look at. I sometimes write it as, I want to look at the columns. Okay, so the columns would be the features, like one feature, but for all the samples. So for example, I have, sometimes I might write it as x tilde. I forgot what I do, but to avoid confusion, x1 tilde would be the first feature, but for everyone. And then the second feature. Okay, sorry, I think, let's see what I actually do. Yeah, okay, so you have to do the other way around, okay? So this is gonna call tilde probably. These are gonna be called tilde. The unfortunate thing is these are gonna be all like you have to do tilde everywhere because the rows I'm gonna represent with tilde, the columns without the tilde, because the columns turn out to be like more interesting for us. So I'm gonna write it as so x1 up to x now p. Okay, so the same thing, like just different notation. So I'm gonna look at the first column. So if you want x1, if you want to be precise, this would be like x 1 1 x. So xij is the jth feature of the ith observation. So this is the notation that I'm going to be consistent about. This I'm okay. So let's do this. It's a little bit tricky. So xj is going to be x1j, x2j up to xnj. So it's the jth feature, but I'm collecting it for everyone. Okay, x1j is the jth feature of the first observation. x2j is the second jth feature of the second observation, and so on. I'm going to call this the xj, the vector. So this is the one that we usually work with rather than the rows. So rows are going to be like all the features from an observation. We'll see that later when we talk about like outliers and just removing one sample. But for the majority of the course, we're going to look at the columns. So the columns are individual features, but for every one. This turns out to have more meaning. Okay, so in this view, let's keep that in mind. Still, I have x beta, capital X beta, but I'm just viewing this as columns. So if I have like that, so sometimes I write x as, so in this one, you'd see I write it as usually as bold 1, sometimes 1n, because now these are in n dimensions. So these are n dimensional. So 1n means the vector of all ones, n dimensional. So that's just this vector. And then I would have x1, which is just the first feature, second feature, and the pth feature. So that's usually what our view of the design matrix. Okay. Still, everything goes true. Like this, these formulas are the same. Just have to like do some of the notation here. These are going to be tilde. The rows are going to be tilde. Everything actually that we did here should be tilde, to be honest. Yeah, like I'm a little bit lazy. I can't go through all of this. Do tilde, let's say. Like different notation for different parts, but from now on, we're going to keep this notation. Okay, and in this notation, I can also write x beta in an interesting fashion, because if you remember, like matrix multiplication, you can multiply rows of x by beta. That's how we did it. Or you can multiply columns, column-wise, if you remember. When we talked about column space or the image, we did column-wise multiplication. So if I want to do column-wise multiplication of this guy, so these are not columns, right? What would happen? Beta 0, 1, beta p. Anyone remembers how to do?
Beta 1 times the first column. That's 1.
It's going to be beta 0 times
Yeah.
this plus beta 1 times x1. Yeah, so beta p times xp. It's true. So does this remind you of some things that we discussed? It's like a general linear combination of the elements, like a general element of the image of x. To see where we're going. So this is the main component of the linear regression model. If I want to write the original model, so this is very important for us. So you can also write it as just compactly as this is just summation, j from 0 to p, beta j xj. Okay. And then you also can rewrite the regression model. If you remember, was like yi is equal to, now we're writing at xi tilde beta plus noise. I can write it as y equal x beta plus epsilon, where y is like y1 up to yn, epsilon is epsilon 1 up to epsilon n. And this part is also equal to summation j from 0 to p beta j xj, where xj's are also in Rn. So this model, everything is in Rn, like all these vectors in Rn. They collect the samples, but these are different views of the same regression model. We often work with this matrix form, with this representation. And in this representation, I have just a vector response. I'm trying to explain it in terms of these vector features. So each feature is a vector. So you can see the regression model alternatively is trying to explain one vector as a linear combination of a bunch of other vectors. Okay. Now when I express y as something in the image or the span of these vectors plus some noise. You can suddenly see the connection with the linear algebra. Okay. So from function view, this is like vector view. Okay. So we're just, instead of trying to explain all the observations separately as just individual ones, we collect them into a vector. Now I just have a vector when I explain this individual vector as the sum of a bunch of other vectors. So this is like linear algebraic view of linear regression. So explaining vector yi as a linear combination of x1 up to xp plus noise, or as an element, or equivalently element of the span of x1 up to xp. So remember, this is a general element in the span, or equivalently as an element of image of x. So image of the x matrix is just, this is of all linear combination of its columns. So what we're doing is we're trying to explain y with an element from the image. So the image of x is our model in this like abstract view. And you're trying to explain this vector, which is probably outside the image of x because of that noise term, by an element in the image. Okay. And you can ask, what is the best in the image that explains this? If you recall, this has a name. What is the best vector? The image is a subspace. Projection. Okay, so that's the idea. So if I want to explain why there's an image, if this is something from the image, I can try to project y onto the image. If you try to do that, exactly back this formulation. Next time I'm going to come and talk about this, but this formulation of these two squares is exactly equivalent to trying to project y onto the image of x. And this gives you the geometric view of these two squares, which is very helpful for us. Okay. So go back, like review projection, image, and stuff like that. Next time we come back and do like use all of this information. So this leads to the geometric interpretation of regression as a projection, I guess projection of y onto image of x. Review that part of the linear algebra lecture. Any questions? Okay, we covered a lot. Next time you come back, like do a bit of recap and then move forward. Thank you.